Okay. Hey, what's up, everybody? Happy Tuesday. Thanks, everyone who could join in. Um, yeah, so my computer's been crashing like a jillion times today. It seems to have finally sorted itself out. So, with luck, we can get through this lesson. So, I'm going to go ahead and start sharing my screen. Actually, hang on, I got to do one thing first. I need to open this Python notebook. So I have the Jurassic Park thing stuck in my head for like no reason. Yep. All right. Good to go. So let me go ahead and share my screen. Sure. All right. Everyone can see the screen. All good.
Yep.
All right. Gosh, money. So today we're going to kind of keep going with feature extraction, feature matching. So last time we talked a little bit about this idea of feature matching, where the goal is, right, you have some sort of object or some sort of feature you want to detect in an image. And we've talked about a lot of different ways to find key points in an image and extract feature vectors from those using things like SIFT and ORB. And so, kind of where we're at now is last time we talked about the idea of where, most feature detection and extraction by and large is just an anomaly detection with extra steps, where this idea is we want to find things that are different from the context, which for us is the image. So the goal is we have this image, we want to find something in that image that kind of meets our requirements so that it's different from everything else around it, so we can kind of figure it out. And so this idea is we calculate our SIFT or our SURF feature vector for our object we want to detect. People usually kind of talk about soccer balls, right? We've talked about that a lot. And then you have your SIFT or your SURF or your ORB outputs inside of the image. And like we've talked about, essentially, SIFT or whatever algorithm you use is going to give you a feature vector for every key point. To match features to sort of detect and classify a feature in the image, we then want to match the feature vectors we pulled out with SIFT or SURF with our feature vector for the thing we want to detect. Right. So we've talked about that a lot. That's kind of where we are in this stage of computer vision. And last time we sort of introduced these three types of feature matching, or really four, but there are three we're going to look at. And those were just a brute force matching, which is essentially taking the distance between feature vectors, the same way you do any other vector where you wanted to sort of calculate how far apart they were in the space. You just, square everything, add everything up, and take the square root. It's just extremely slow when you have a feature vector with like 1028 values in it. So like pretty much everything in computer science, brute force works, but it's never the right way because it's usually pretty slow. So the first sort of better version we're going to talk about for class is FLAN. So FLAN stands for Fast Library for Approximate Nearest Neighbors. So to kind of reiterate what I was just saying, we have this idea where we know how to find features with kind of our low-level algorithms we talked about with edge detection and view transforms. We talked about extracting features with sift and surf, like I was just saying. So the thing to remember as we go forward with feature matching is that we have to extract key points first. So feature matching and object detection and classification isn't a different kind of algorithm like sift or surf. It's, sometimes people can get a little tripped up by that, where sift and surf are pulling out features. So I have features, right? And like Flan and some of the others we'll talk about, like YOLO, also pick out features. So the idea is a lot of people have was, you can sort of run feature extraction without first, or run feature matching without first running a feature extraction algorithm. So when we talk about these things going forward, just know that we have run some form of sift or surf or similar key point extraction algorithm before we start trying to match features. So the feature matching algorithms we're talking about, to kind of put that differently, FLAN won't extract key points. FLAN will only test your feature vector against the key points someone else has already extracted, right? So we sort of have to do all of the legwork to get to a point where we can even start doing feature matching, which is understanding what we've done so far with, filters and the different kinds of thresholding we've done, and then the different ways we can kind of pick up edges and primitives. So we've sort of done all of those things to get ready for, our sort of final phase of computer vision or a big application, where we're doing object detection and object classification and, anomaly detection and all these different things. So the idea is we've already run an algorithm that has given us key points. So we've run our algorithm, we've got our key points, and what we go on to now is this idea of, now we're looking at the high level feature detection or matching or extraction. There are a lot of words that get thrown around a lot. And I apologize if it gets a little confusing, but again, it's just this idea that we found interesting stuff, and now out of all of those interesting things, I want to find my specific thing. And so the first version of that we're going to talk about is FLAN, which is the fast library for approximate nearest neighbors. So some of FLAN gets very linear algebra-y, especially, well, we'll see as we go. So at this point, it's kind of, we could spend a couple weeks just talking about the linear algebra behind FLAN and the statistics behind it. Or we can kind of cut out some of the middlemen and care a little more about what it can do for us in computer vision. So for kind of the next algorithms, I'm not really planning on going into as much detail as, say, creating our own canny edge detector from our own kernel, right? We're not really going to create any of our own bits and pieces of FLAN unless, we want to for some reason. But the idea is you want to do nearest neighbor search, which you guys are all probably likely more familiar with than even I am from my background. But right, this idea is Flan isn't built for computer vision. It isn't just a computer vision algorithm. It's super, super good for computer vision, but you can use it for a lot of different machine learning types of tasks. Like you can use Flan for sentiment analysis and text data if you were so inclined. It's essentially just an algorithm built to work with very high dimensional spaces. And embeddings for like a language model is a very high dimensional space, and feature vectors for an image are a very high dimensional space, as along with other things. So kind of keep in mind, Flan wasn't built for computer vision. It works very well for computer vision. And if you kind of have a good understanding of the model itself, you can use it for other things quite well. But anyway, all that to say, the whole point is I have this really big multi-dimensional space, and I want to find who is closest to the data points I care about. So, right, like in sentiment analysis, it would be which words or which tokens are closest to happy and which are closest to sad or whatever. For us in our high dimensional space, it's our feature vectors. So we have this space and we have sort of the thing we care about, our source. And what Flan then does is it looks at the nearest neighbors to that point, and it uses an approximate search. And that's kind of the stuff I don't want to talk about too much, but it mostly uses trees or hashing. But the idea is, we could do an exact search, which is basically a brute force search, which is sort of a version of Flan where, the neighborhood you're looking in is everywhere, right? You can kind of think of it as what if, we took brute force and then just clipped a bunch of the stuff that's too far away from what I care about. And we find the stuff to clip by sort of starting where we want to be and then only testing the things that are around us until we kind of get too far away, essentially. And so, like a lot of things in computer science, the idea is we want to approximate it so we can figure out, we don't need a good answer, we need a good enough answer is kind of the deal. And so you can kind of start here with Flan and then tinker around with the parameters that define good enough. So, and next time I had more, I was going to get ready for today, but then my computer crashed about 70 times. I got it to boot up like literally 15 minutes ago. So I have some more stuff to show, but not as much as I planned. But anyway, where I was going with that is Flan is a lot like K nearest neighbor, so KNN. KNN is, again, just sort of a version of Flan where we have this parameter K that tells us a little more about how we want to search for our neighbors. So Flan and brute force and K-nearest neighbors all sort of live under the same umbrella of an approximate search to find the closest points to our target point in the feature space. And so it kind of does this in these ways. So, before we can call Flan or KNN with OpenCV, we do have to first call SIFT or ORB or some other implementation of a key point extractor, essentially. Then what it does is it matches features. And so I said, I don't want to talk a lot about that because it gets pretty wacky. But the idea is you have some different tree search algorithms, you have some hashing techniques, but the idea is, I know where my starting point is with my starting, feature vector I'm trying to match, and I just look at the nearest things until I stop finding things that are close enough for me to, want to include them or care about them. And then after Flan does that, there's some different ways to remove outliers or noise. Like any approximate search, and especially like a nearest neighbor search, you have a high probability of false alarms or outliers or just sort of noise. And, this is something, if you think about like countermine operations or counter UXO or whatever, where you're using a radar to find something you don't want to drive over, you're using a radar to find, airplane flying around. There's a lot of false alarms. So in applications, you'll hear things like FAR or false alarm rate. And that's just sort of a fancier extension of something like Ransack, which is what Flan uses, which we can talk a little more in detail Thursday. But it's essentially a outlier detection and reduction algorithm. Like I said, there's a lot of options. There's FAR algorithms you can look at. Flan sort of comes with this Ransack algorithm. It's kind of the default, which is just a random simple consensus version, which it's a neat algorithm, essentially, right? It just picks a random point that it thinks matches the feature vector and then kind of asks all of the points I've already decided are close enough to the feature vector if they think it's close enough. Obviously the data points aren't thinking, but it's like some of the convolutional kernels we looked at where, all of the points sort of inside my cluster I'm looking at get a say if in terms of, whatever points are near to us or farther from kind of the consensus. It's like how the hue transform works, or the Hue transform, right? Where line points sort of get to vote on whether or not this pixel of edge is part of their bigger line or a smaller line somewhere else. And so after it does this for us, we give it the output of SIFT, and then it matches features, removes outliers and noise, and then it gives us back which pixels or objects in the scene match the target. They match what I've said I wanted to find. And then the next step after that is again, outside of Flan itself, you have to come back around with another algorithm or some different methods to image stitching, which is essentially, putting what you found back into the image. It's just sort of taking the things you've detected, putting them inside the broader image, and then sort of marking them somehow. So, image stitching is sort of like if I have a traffic light camera that's detecting cars, then, Flan gives me back where in the image it thinks a car is, and then, it's another step kind of up the CV ladder to then draw the box that's around it, moves around while the car moves around. But it's essentially just a contextualizing of the things you found. So that going to, sorry, yeah, all right. All right. So let me pull this up. So I put together a notebook for Flan. Obviously, I'm going to keep working on this because, like I said, I had some issues for about half an hour trying to get stuff to work that I might have honestly been because of Steam, which is insanely bad for how insanely many things it does. I don't know if I've ever opened Steam without having to update it. That's significantly worse on the Steam Deck, but it's also super cool. And none of that has anything to do with computer vision. So let us look at some quick and dirty applications of Flan. So what I'm trying to do is just a real, you know, common computer vision task where I want to detect a stop sign. So I start here from, my sample image. So this is where I start. And I'm going to apply my sift or orb to this and ask it for all of the key points it finds inside of a stop sign. Right. And then once I have that, I'm then going to give it this image and say, hey, do sift or orb on this image and find me all the key points. And then find all of the key points in this image that match all of the key points in this image, right? And in theory, this will just find me a stop sign, quick, easy, no problem. So the first thing I've got is you can see BF Matcher. So OpenCV does have a brute force matching algorithm. Like I said, it's essentially Flan, but the neighborhood is everything. So it's still checking everything, essentially, well, not essentially, it's brute force. So you can see in the code, right, we bring in our two images. So we want to look at the source stop sign and the target that we're looking for. And you can see, so here's the step where before we can do anything, we have to run sift. And right, we've learned up until now that it's not as trivial as this, right? We've talked about all the different things that go into a sift or an orb algorithm and how they can affect the key points we get. So right out the gate, it's very safe to assume our performance will be very bad because we've just thrown sift at it completely devoid of any intelligent sort of optimization or parameterization. And so, we've got the basic out of the box sift algorithm. And then we're going to find, right, we've got our key points for our source stop sign. We've got our key points for our target stop sign we're trying to find. And then we can just hit it with this brute force matching algorithm and then just sort of, for the sake of tracking things, I've got it timing, how long this is taking to run. And then you can see for our good matches, we're essentially, right, again, real dumb. We're just saying if the key point from image 2 is 70% of or 70% close to, right, our target, then I'm going to say it's a good match. So this is just, like I said, it's really dumb, but it works. It's our essentially our threshold and parameter to say everything that's at least 70% similar or closer than this 30% distance, we're going to say is a match. And then we can go in and look at them. So start this before we start running through it. So if I want to use just brute force, let's see, think for a minute. All right. So here you can see with our brute force matching, it only took 0.04 seconds. So we saw it was super fast. But you can also see because we've just let OpenCV do whatever it wants, kind of free reign, our matched features are terrible. There's just we have two features that are matched on the stop sign. And then, it can't tell the difference between some of the white lines outlining the stop sign and the white lines on the road. And the kind of white reflective stuff on the pole there you see is also throwing it off. And the fact that our target image had a white background can also have an impact on this, because it looks for lighter colored things, because a huge part of what I've given it is, the color white. So that was our brute force method. If we want to get a little smarter, then we've still got our same just stupid generic SIFT algorithm finding our key points. You can see for our flame direct parameters, it's doing 5 trees, so that's kind of the number of trees it's searching through for the approximation. Again, you guys probably already know way more about that than me. So it's just looking through these 5 different sort of trees, and it's checking, in this case, 50 times to see if stuff matches. And so you see, you have your flame-based matcher, and you've got, your algorithm, your number of trees, your number of checks, and it's just going to go through, and everything that meets the descriptions and falls within our flan match, then we're gonna say it's a feature. And the reason I said this is sort of a version of a K nearest neighbors, and you can even see, right, our flan KNN match with K equals 2. We're going to talk about that next time. But K nearest neighbors, like I said, is just K is a parameter that determines how things are related and how much or how close it has to be. So we'll talk a little more about that next time, but just, you can see already flame is just KNN with extra steps, essentially, or KNN is flame with extra steps, depending on how you want to look at it. Here you can see, though, we've got kind of the end result is the same. We're still going to say 70% similar. And we're just doing the search in an approximate way instead of a brute force way, right? Okay. So if I run this, what happens is it actually, with the flan, it took longer, and you can see why, because the way we set it up, everything is a key point in our target image. It's just bonkers amounts of noise. The entire ground is key points, the entire background is key points, and it finds the same amount of key points on our stop sign, more or less, maybe a few more on the stop sign. Yeah, 3, 4 more. And it ran an order of magnitude slower. And this is because of, the fact that we did not do this step in a smart way, right? We did that step in a very simple way that didn't care about what the image actually looked like. And then we did our flame parameters, again, in just not a particularly good way. And then we defined our good matches at the end as still kind of the same as from before. So we end up with just a tremendously noisy image that runs an order of magnitude slow, which kind of defeats the whole purpose. So then kind of the immediate question is, okay, why? Why did this not work? And it's a function of both, we were stupid with our parameters, and also because it's a very simple image. So if I'm only looking at a few key points, I can do brute force pretty easily. If I'm looking at a few key points with flan, then I'm still doing way more searches for way less key points. And so it takes longer in this case to test every key point for that neighborhood property with kind of the approximate search that gives us a bunch of stuff than it was with just the brute force search and one silly parameter. So if we look at, doing brute force matching for a more complicated scene, you can see it runs really fast because it doesn't find anything. Right now, we want to find our stop signs in our bigger, more important image, and instead, I don't find anything, even though there are obviously two very clear stop signs right on the road. So even for super easy tasks, just picking stuff up out of OpenCV and applying them without knowing about what's going on, I know we've talked about this about 1,000 times this semester, but there's all kinds of choices made with our source image or stop sign in the top left there, and all kinds of choices we make in SIFT and SURF and how we find our first set of key points, and all kinds of choices we make when we apply something like FLAN to match our key points. And those choices matter, and we have to build these things in a smart way, right? And I can just copy paste this and see how the FLAN runs. Complicated thing. And you can see that much like last time, our better, faster algorithm ran slower and the output looks awesome. So next class, when we get together, I'll run through KNN and probably YOLO, you only look once, is the kind of other big one people use a lot, and then kind of pick apart the things happening with the false alarm detection, kind of the denoising step, and the parameterization of the nearest neighbor search, and how, we can go from this nightmare sea of key points to something of value for an actual computer vision task. But the main thing is, even for something just as dead simple as this, there's a lot to think about and understand. So that is pretty much what I had for today. Said I was kind of in the middle of preparing stuff when my computer tried to vomit and die. So I'm going to go ahead and wrap up there. I'll get all this stuff dumped onto my courses, and we'll cover some more stuff in some more detail next class. All right. So everybody good? Dope. All right. Y'all have a good day. Happy Wednesday too, I guess. And I will see y'all later.
Professor, I have a question after, uh, just for like personal, I guess.
Sure.
I don't think I'll make it to class on Thursday. I remember you mentioned that the project might be assigned. Is there anything I should know now just to prepare for it?
No, because I'm still figuring out what it's going to be.
Okay, so just hang tight until next
Yeah,
Tuesday.
yeah. Just stand by.
Awesome. Sounds good. Thank you.
Yep. Killer. See you guys later.
Thank you, Professor.